All right, let's get started, folks. So, welcome. Thank you for joining us today to get an insightful look at Matrox Imaging's deep learning technology, which comes included with the newest iteration of Mill and Design Assistant software. So, before we get started, allow me to take a minute to introduce our main presenter for today, Mr. George Chang. George is one of the most experienced engineers here at Matrox Imaging, holding well over 20 years experience in machine vision. He started his journey here at Matrox as an applications engineer, but now acts as territory sales manager for the US Southeast, as well as for Central and South America. My name is Timothy Labrie Cameron. I serve as lead inside sales for North America. I help to support new business development and marketing initiatives here at Matrox, including moderating webinars such as these. But if you're reaching out to us with an inquiry, chances are I'm the one coordinating the response. So as mentioned, today we're going to be taking a dive into deep learning. More than just an obvious buzzword, deep learning AI has already demonstrated to be a hugely successful tool at tackling applications that have otherwise proven unfeasible for conventional machine vision tools. We at Matrox Imaging have developed a very robust, highly versatile, and accurate deep learning algorithm that aims to make those impractical applications a thing of the past. So today we intend to walk you through the process from a bird's eye level and showcase its ease of use. So during the presentation, feel free to plug in any questions if you use the chat function to the right of your screen. And we're going to conduct a short Q&A after the presentation. So if for any reason we don't get a chance to address your question during the Q&A, don't worry, we're going to follow up with you personally afterwards via email as well. Lastly, this webinar is being recorded, so for those of you who don't have a chance to join us today, it will be made available for offline viewing. So with that, I will proudly hand the microphone over to George. George?
Great, thanks, Tim. Just to check sound, is it okay? Are you able to hear me?
Loud and clear, sir.
Excellent. Well, once again, welcome everyone, and thanks for joining us in today's webinar, where we will talk about deep learning. We're going to share a couple of tips and tricks and look at some practical examples on this topic. As Tim said, my name is George Chang. I'm a territory manager in Matrox Technologies. And for the folks who might not be familiar with Matrox yet, we're a Canadian company with over 45 years of expertise in the design and manufacture of hardware and software component solutions in the imaging and graphics industry. I've been doing that for 45 years. We're headquartered here in Montreal, Canada, where we house our own engineering, R&D, manufacturing, sales, and marketing. But we're also a global company. We have offices in Europe, Asia, and our headquarters here in North America, and representatives in over 20 different countries. Today, Matrox is part of Zebra Technologies, a market leader in scanning devices and technologies. Maybe a little known fact about Matrox, we hold over 120 patents related to machine vision. And we're part of the group that is responsible of specifying standards such as GigaVision and Coax Express. So when you're working with Matrox Imaging, you're not dealing only with a global supplier, but also a company that is driving the future of machine vision and the innovation in machine vision. Today, there's a broad range of industries that rely on Matrox technology, anything from medical imaging, automotive manufacturing, electronics, food and beverage, pharma, logistics, semiconductor, with a lot of major Fortune 500 companies backing up some of our tools. A general overview of the Matrox product lineup: we have our software at the heart of it. We have the Matrox Imaging Library, which is a programmer's C, C++, C#.NET library with functions for anything in machine vision, things like pattern recognition, blob analysis, barcode reading. And our second package, it's called Design Assistant. This is a flowchart-based programming interface that enables you to build applications by simply configuring a flowchart. And in this webinar, we'll tackle a little bit more closely Design Assistant than Mill. And one of the very great features of our software packages is that it enables you to deploy applications in different type of Matrox platforms. Anything from smart cameras like the Iris GTX, frame grabbers, vision controllers, and build applications on 3D imaging with the Matrox Altice profiler. So more specifically on Design Assistant, like we mentioned, it is a flowchart-based programming environment. It enables you to configure acquisition, inspection, PLC communications, and controls. Not only that, it also enables you to build 2D, 3D, and also deep learning applications. So as a vision professional or as a controls engineer, it's very useful to be able to tackle all this type of technologies or applications with the same interface. But just as interesting as the image processing part of it, you can also build a data storage and archiving model that enables you to store pass and fail images, as well as to build your own customized operator interface, right? The interface to your application. And like I mentioned, the same interface enables you to build systems that can be deployed to our smart camera, like the Iris GTR or GTX, our latest generation smart camera. And this becomes a headless device, an autonomous device that once is deployed, is able to do inspection. You can also build applications that can be deployed to a Matrox industrial PC, like the Foresight EV6. And for example, grab from one or multiple area or line scan cameras or thermal cameras, for example, or even 3D applications with the Matrox Altice profiler. And finally, also deploy on a Matrox Foresight XV6. This is a desktop grade computer with slots in the back that enable you to plug in frame grabbers or capture cards. In this case, we can interface to a Coax Express card, enables you to grab from high-speed area or line scan cameras, for example. So again, the key thing or the key takeaway is that it's a very simple interface, and you will have the chance to build applications that can be deployed on all these different platforms. And a key thing of Design Assistant, it's this capability of branching and conditioning, right? A lot of the tools out there that are easy to program, they typically do what we call linear programming, right? So basically take a picture, add 3 or 4 tools, and get a result and activate an IO. And that's what we can do with Design Assistant, certainly. But in Design Assistant, we have a few branching and conditioning objects that can be plugged in into your flow that will enable you to build fairly advanced applications, right? For example, coming in from a branch and then depending on the result, branching out to other branches and applying different tools depending on that first option, right? So again, very advanced projects can be built with our flowchart interface. And a typical workflow, just to give you an idea of how you build applications in the case of deploying to an Iris GTR, you have Design Assistant installed on your laptop. You build an application through our flowchart screen where you plug in the logic. Obviously, the output of a tool or a step or a little block that you see over there can be the input of the next tool. And with that, you build out the logic on the flowchart. Not only that, you get a chance to have live results, numerical results, and be able to debug your application with the interface. You can then build a customized operator view. Operator views are web-based. There's a web server inside the platform that will be publishing this sort of interface with your operators. You can customize it with different layouts, different images. You can plug in pass-fail results, numerical results from your application or your tools. You can have different buttons and navigate to different pages. So it's, again, fully customizable, making the solution your own. And that's it. Once you're satisfied with that, you deploy the application to the platform, in this case, the Iris GTX, and you don't need a PC anymore. The Iris becomes your inspection device. It is a standing there, standalone, taking pictures, uh, doing the inspection, and also activating either IOs or talking to PLCs. Again, all within a very compact system that is also IP67, right? So it's wash down and dust proof as well. In the case of a foresight, it's a similar concept, right? You deploy the project, in this case locally, because the computer, the foresight, has the development environment as well. And once it's deployed, again, you will be able to execute the inspection, and not only that, perhaps use a multi-camera system to build this application, right? And in terms of the HMI pages, you're able to look at different options, different buttons, and different images as well. Today, there's a wealth of global solutions that have been deployed with Matrox technology, anything from reading codes at PepsiCo, or doing pick and place on Bosch machines, or inspecting filters for motors at Still, for those big cutters, for example. They can all be deployed using Matrox technology. So into the topic of today, which is deep learning. We'll start with a little bit of terminology. So what is deep learning? They say that deep learning is or artificial intelligence is a key component of Industry 4.0. This is in addition to cloud computing, robotics, wireless, and IoT. But we hear a lot of artificial intelligence, machine learning, and deep learning. So maybe just to give you a little bit of background, artificial intelligence is defined as any technique that enables a computer to mimic human intelligence. So could be something as a simple program with if statements, for example, if it's raining, use an umbrella. If it's sunny, then use sunglasses, for example. So that could be cataloged as artificial intelligence. Now, a subset of artificial intelligence is machine learning. And in machine learning, we have part of the process, which is a feature extraction, right? And this is done by humans. So humans can extract or type in or catalog features of an image, or in this case, this is the input, pass it through a classifier, and have an output to determine if, for example, the image is a car or not a car, for example. That could be the output, right? So that is machine learning. And then a subset of machine learning is what we call deep learning. And in deep learning, the feature extraction portion is done by software. So there's no human required to extract features to then be passed into a classificator or a classifier. In this case, again, to determine if the image we're seeing is that of a car or maybe not a car, right? However, in the industry, we use quite interchangeably these different terms to denote deep learning. So a lot of times you might hear machine learning, and in reality, we're talking about deep learning. So just to keep that in mind. And this classifier, this classificator, it's what we call a neural net. It's some people call it a black box, but it's essentially a classifier that will drive an input to a specific output. And there's many types of neural nets in the industry. There's neural nets to, for example, predict what product you would be most likely to purchase, right? If you shop online, for example, that is the kind of things that certain neural nets do. There's other neural nets that that are specialized on speech recognition or human speech recognition, right? So we all know about Alexa and recently the Lambda project in at Google, right? So those are different types of neural nets. The one that we use in machine vision for images is called a convolutional neural net, or a CNN. And in the reason why it's because the first part, the feature extraction portion done by the software, we use a convolution to take an image and basically extract features of it, which when we pass to a classifier or a classificator, gives us the output, right? And that is what the CNN that you'll hear about it's referring to. So this classifier, this classificator is based or is composed of different factors and weight factors and bias factors that will determine the path from the input to the output, right? So this is when we talk about CNN is what we're referring to. But when it comes to machine vision, again, what is the role of deep learning in machine vision? Well, it's all about classification, right? So we're classifying images as to they belonging to a pass or fail, go or no go. We can classify regions, or even we can classify pixels at the pixel level to which category something belongs to. So it's all about classification. And deep learning is able to analyze very complex images and account for different variations like light variation, part placement, small part movement, very tiny features. So what we call acceptable variances, right? So that's something that the deep learning technology is able to help us basically classify and see if this belongs to either the pass or the fail category. But one key thing is that it does require very careful data preparation and training, right? So the result or the success of our neural net or CNN depends highly on the data. How is it captured? How representative it is, right, from the end application. But we have to keep in mind that at the end of the day, it's still a probability calculation, right? You will hear this term inference or inference speed or inference score. And what we're talking about is the prediction score or the prediction speed. So you'll hear that term often when we talk about deep learning. So in the typical workflow of a deep learning application, it all starts, like we mentioned, with data collection. So we have our hardware, our smart cameras, our computers that can be plugged into your production floor and start taking images or taking sample images. And what's key again here is that we need images from the field. Sometimes we run into applications where images are taken in a lab environment. There's a CNN trained, but then when it's deployed, there's some variations are not taken into account that it's seen on the field, and then we run into some problems. So we have to retrain. So very key thing is data has to be captured from the field. That's very key, a very important aspect of it. The second step is what we call labeling and training. Once you take the data, the images, we need to basically categorize or tag each image as to which category it belongs to. Sometimes it's called the ground truth, right? So in this case, we'll have an example. We'll see 3 different types of fabric types, and we need to label them and assign a ground truth to each sample image. The next step is the actual training itself, and we'll see the tool we use for training. Actually, it's called Copilot. We'll see an example on that. And training, again, ideally, it's done on a dedicated hardware with the GPU to shorten the training time, right? So depending on the number of images, this can take between days to perhaps weeks. A GPU will certainly shorten that processing time. And once the neural net has been trained and tested, we go to the deployment process. And that's where we can use the Sign Assistant to build an application and then, again, plug in a CNN step to take an image, classify it, and then based on that result, branch out to different routes. And let's say after a few months, the project it's been monitored, it's been doing good. You also end up with a lot of data that has been acquired and classified correctly. You may want to make your CNN a lot smarter. The way we do that is by a process called fine tuning. Let's say every 6 months, you may want to take the data that's been processed, acquired, and archived, and then retraining your CNN to make it a lot smarter, right? And that's the way that CNNs sort of become more precise, if you will. So that's the whole sort of workflow of a typical machine vision deep learning application. So there's two types of deep learning technologies available in the Matrox software. One is called global classification, where we use it to classify an entire image. So for example, good use cases of this would be to take images of parts and then classify them as either being a go or no go, or good or bad, presence or absence of a feature, or part is correctly assembled or incorrectly assembled, or maybe categorize it into good and different types of defects, right? So defect type 1, defect type 2, and defect type 3, or maybe just to classify product types, right? You have, maybe a manufacturer of food manufacturer, let's say pizzas, right? Coming at different toppings, right? There's no real pattern for what a margarita pizza might look like versus a Hawaiian pizza. So that's where, again, deep learning comes in and would be able to help you classify into the different types of product, or even for robotics, sometimes pick and place applications, depending on how the product is positioned. A CNN can be trained to recognize, right, different possible positions of an object, and therefore drive a robot to that. So that's what we call global classification. The other type of deep learning form that we support is called segmentation. And here, what we do is we're able to locate and identify a feature or a defect on a product, right? To locate that where it is. We can actually, again, use cases are locating foreign material on products. So for example, meat processing, you may want to look for foreign material like wood chips or whatnot. This could be a tool to actually tell you where that foreign material is. Again, not just the location, but also the counting and also sizing of the feature or defect. And also as an end result, perhaps grading a product based on the quantity or the presence or absence of these features, right? So those are the use cases for the segmentation form of deep learning. And in terms of images, again, we have, for example, in global classification, we are presented with an image. There's two types of meshes, for example, that are the two categories, and this can belong to the valid or defective mesh. This is an example we'll see later on. We have a PCB with four possible categories. One would be a good board. Another one would present some foreign parts or extra parts. There's another category that might show paste, soldering paste on the PCB, or maybe some scratches on some of the chips, right? So these are four categories, and the end result of global classification is to tell you which of these categories the image or the part essentially belongs to. Now, in segmentation, we mentioned we're able to locate the feature itself. In this case, this is a metal plate with possible dimples or scratches, and during segmentation, we're able to tell you where exactly it is. Here's another example we will show later on. This is a plank of plywood, and then basically, depending on the number of knots or maybe the size of the knots, the whole plywood can be considered of different grades, right? So by using segmentation, we would be able to determine this. And again, to reiterate, global classification, the label and training is done on the whole image. The classification, again, it's returned over the whole image. And the output is a best class or the class with the highest score, right? So that would be global classification. In coarse segmentation, we have the labeling process requires you to use a digital pencil to mark out the different classes or categories present in the image. So background would be one, for example. In this case, we have large knots that are annotated with a, let's say, a red mark, and small knots annotated with a blue mark, for example. The training, again, internally, there's an algorithm that will generate tiles, and the classification process also, again, internally, there's a smart tile that would be moving through the ROI. But what's interesting is the output. Resulting output is a image map with pixels corresponding to the different classes. Now, this image map can then pass on to another step, like blob analysis, which then would enable us to classify or count or size up some of these knots, right? So this is the sort of a overview of the two different technologies, right? So a little bit more details on the labeling process, labeling the data sets, and the process of training using Copilot. Copilot is a tool that enables you to train a CNN. It has functions for batch processing, sometimes required to condition an image, for example, scaling or creating an offset on an image, resizing the image, or maybe cropping an image to where an ROI or where the object of interest is. So you have those tools, but over and beyond, Copilot enables you to generate a CNN, do the labeling, the training, and also the testing of your CNN. One key thing also is that at some points where maybe you do not have sufficient images for a data set, for example, Copilot also have tools for what we call data augmentation, right? So taking an image that you capture from the field and artificially adding some variations to it. So some of these variations could be lighting variations, right? Maybe adding some lighting unevenness, maybe moving or translating or rotating the image by a few degrees, again, adding a little bit more of that potential variation on the field. So that's something that you can leverage from Copilot to enhance your data set. And with the Matrox software, we have an example where with a complete set of data sets that shows you how to build a CNN to classify three types of fabric. In this case, we have fabric 1, 2, and 3. We present an image, and the example will basically tell you to which of these three types of fabrics the image corresponds to, giving you also a score, right? What's the probability score that it belongs to this class, right? And how we do it? Well, it all starts first of all with data preparation, right? Typically, you have different folders. In this case, we have sorry about that. We have 3 different folders, each folder containing 50, 100 images of each type of fabric. We have fabric 1, 2, and 3, and each one has, again, samples of the 3 different types of fabric. And then we load them up in our Copilot. We add images with the Add Image button. Copilot will automatically generate the 3 different classes based on the name of your folder, right? We will also create labels for it, and we will actually load images and automatically label them with the type of fabric it is. And not only that, obviously, we have a little sort of color code to quickly allow you to identify which category it belongs to during the labeling process, as well as taking a little thumbnail for that. Once images are loaded, all you have to do is to accept and click on the train button. And once you train, that's where we see our neural net, our CNN, come to life, right? It's taking the data sets, the hundreds of images, trying to find the most optimal weight. I don't know, remember there was those weight factors on our CNN. And the idea is at the end of the training, we should be heading towards zero errors. So you essentially, when you see this sort of curve heading towards zero, meaning zero errors, that means that your CNN is smart enough, at least with the data set that you presented, and is able to at least try to tackle images from the field, right? So that's the whole concept of this training. Once you're done with the training, Copilot presents to you a few statistics of your whole training process. You will also be presented with what's called a confusion matrix. So basically telling you or showing you how many, in this case, fabrics predicted correctly, right? Fabric 2 was predicted as fabric true. And in this case, fabric 3, we saw that only 59 out of the 60 was correctly predicted. There was one that was incorrectly predicted. And again, depending on your data set, this might be okay, or maybe you want to fine tune it a little bit more. Again, this is what the confusion matrix tells you. And a bunch of charts telling you, again, the number of classes there are, number of images, and the distribution of scores on your application, on your training, right? So once you're done with that, again, we're satisfied with our CNN. We have tested it. We've seen that a lot of the predictions are done correctly. We end up with a file. A CNN is called an M class file. This file is the one that you then plug into or import into your design assistant project with a CNN step, class index step. And basically that's it. Here's the design assistant on development. We're able to take a picture. We're presented with an image. The classifier, which is this step, will tell us which of the 3 classes has the highest score. In this case, Fabric 2 has 99% score. And we can actually just roughly see that it is Fabric 2. These are thumbnails of the different classes, and so on and so forth. So with this, again, as you can see, you can easily build a machine vision application that makes use of this deep learning technology and be able to test it. And again, once you're happy with the testing, you click on the deploy button and you end up with a runtime application with a trigger waiting for the part to come in, classifying the image, and then maybe activating an IO, for example, right? So all that is a quick overview of the I guess the theory and the workflow of deep learning. In this section, we'll briefly go over 3 practical examples of this deep learning technology. This first one we're seeing over here is, as we mentioned, is a PCB or printed circuit board inspection or classification using deep learning. We trained a CNN with about 60 to 70 images per class. We have 4 different classes. One is the good board, where you have no defects. Another type of samples or class was PCBs with extra parts. Another one was we have paste, and you'll see some images with soldering paste somewhere. And the final category was one with scratches. We added a little bit of transparent tape, right? Which would be very difficult to detect using traditional machine vision. And in this case, again, what it's giving us is at least the project, the deploy project, and the operator view that we put together was showing us the part with the highest score, in this case, good board. We annotated that on the image itself. We will then go ahead and load the next image. And in this case, we have extra parts. Sometimes even for me, it's really difficult to see where these are, but I mean, we can actually see them over here. We have extra parts. This one, we have tape. You see over here, tape. This one is good. Again, more tape. This is extra part. And again, this is actually being executed right now in my PC with images are loaded. And what's interesting, again, it's the complexity of the images. These are really complex images with a lot of details. Illumination is not even. There's parts, even some ICs with different labels or silk screen or annotations. And yet the neural net was trained and was smart enough to determine, predicting accurately which of these categories the PCB or the piece or the part right now belongs to, right? So this is one example, again, very impressive. Again, we're talking about what are acceptable variations, right? We talk about, maybe if a little resistor is a bit off, twisted slightly, that's still okay. And that's what the deep learning algorithm is able to help us with. The second example we have over here is that of a bottle inspection. A lot of recycling or bottle recycling projects and processes require you to look at, the lip of the bottle, because obviously that's where, someone might get hurt if they drink the product. And in this case, we have, again, three different categories: good, scuffed, which is still acceptable, and then chipped, which has to be rejected, right? So in this example, we load an image, or we take an image, we look at the image, and then we classify based on CNN, again, trained with about 50 images per class. We use a bit of data augmentation in this example to complete our data set. But as you can see, we're able to correctly classify if the bottle is good, scuffed, or chipped in this case, right? In this example, we actually use a traditional machine vision tool called Circle Finder to, first of all, locate the lip of the bottle, which is a circle, and then apply a classification on that area. So that's what we do over here, right? So, and this could be running on your application on your bottling inspection line as such, right? And finally, a third example. This one is using segmentation. Again, we have two different categories. Well, actually three. We count the background. We have large knots, small knots, and we then, once we train the image, we train the neural net, we load an image or capture an image, and we're able to locate, at least here it's color coded, the location of the knots, as well as characterizing the sizes of each, right? Small knots, large knots, how many there are. And then based on this, we can then, sell this at a more expensive premium price because it has only small knots or no knots, or maybe at a lower grade based on, right, the presence of that. So these are three practical examples where deep learning or machine learning is able to help us with the applications, right? So now that we've seen that, we're going to share a bit of strategies, additional strategies when building your application using deep learning. For example, if we have presence of multiple types of defects on the same part or the same image, well, we use a technique called the one versus all. It's a technique. It's very simple, actually. The idea is to create multiple CNNs, multiple neural nets, having two classes, either the presence or the absence or the not presence of that feature. So for example, in this case, I have a set of images that has soldering paste. So as long as it has soldering paste, it belongs to my presence class, right? It can have other defects. It doesn't matter as long as it's there. And the other set of images for the not presence class would be, again, the absence of that. It could be good. It could have anything. But as long as there's no soldering paste, it doesn't belong to the not present class. And once we train that, we have one CNN. And then we do that for, again, all the different potential defects or defects in the image. And at the end, we combine, right? We combine all of them, and then we have the result of the presence or absence of multiple type of defects on the same image. So that's one strategy. Another strategy that we use is that rather than doing a global classification on the whole image, what we do is we use a fixturing tool like pattern matching or maybe blob to locate the part and then apply a classifier on an ROI, right? In this case, we see this mechanical part, we fixture it, and we apply 4 different CNNs, each one corresponding to a different type of pass-fail for that region, and CNNs can be applied to small regions as well. And the overall result of the image of a pass or fail will depend on all this ROIs passing, right? So that's the whole idea. And again, the flowchart coincidentally would look the same, except that in this case, each CNN would correspond to different regions of the part, right? So that's another strategy we use. Finally, some speed improvements. Again, the idea is to run this on our smart camera, on our PC. A lot of times we have too much data that is unnecessary. For that, we always suggest to either resize or crop the image or subsample the image to a size that it's still usable. Of course, there's a point where you subsample too much, your features no longer there. But that's a separate story. But again, the idea is sometimes you do not need that much of a size to run CNN training. We also suggest to use monochrome images. A lot of times, we know unless color has an influence on the defects, a lot of times a monochrome image is sufficient. So if you end up with color images, we may suggest you to convert them to grayscale. And finally, again, we showed that on the bottle inspection or the lip inspection tool, where we use a fixturing tool to locate a part and then just classify an ROI, right? There's no need of classifying the whole image when we can narrow it down to a specific part. And these are some of the tips that we typically use for improving the speeds on applications. Other key thing is to make sure that your data set is balanced. We don't want to end up with 100 images in one class and maybe 10 images on the defective class, right? Because that will create a sort of like a bias. And again, ideally, generate images that have defects so that you have an equal amount of good and bad parts or good and bad images. And in addition to that, again, use Copilot for data augmentation, right? So add small variations to your images are taken. And something we mentioned at the beginning, make sure that you take representative images. Images are representative of the parts from the field. Because again, a lot of times a lab environment is not necessarily the same as your environment in the production line. And we saw that with the bottle inspection. Okay, so we talked about the hardware, about the software on deep learning, and it's all great, but you still need hardware, right? So for the development on the training of the CNN, we recommend to use a GPU. Copilot, you have the option of training your CNN on a GPU platform, and Matrox actually offers a system that is dedicated or customized for CNN training. So it's a Foresight XV6 DL that features an pre-installed NVIDIA Quadro RTX 4000 solid state drive and comes pre-installed with Mill and Design Assistant. So you're able to do the training there. And again, it will shorten your training time from days to hours, perhaps, right? And again, it's a constant process. Sometimes you may need to try this 2, 3, 4 times until you get a good result on your CNN. It's all dependent on your data set. And the GPU will enable you to speed up that trial and error. The other option is to use your own PCs and purchase Design Assistant. I do not recommend using your laptop for training. I know we have some customers that have laptops that have GPUs, but they're not the same grade as your your desktop grade GPUs. And yeah, you'll be spending a lot of time waiting for the neural net to be trained, right? So that's in terms of the development aspect of the training of the neural net. Now, once you have the training, we talk about runtimes. Option number one, you can deploy your application on our Foresight, which can have cameras attached to it, multiple cameras. Option number two would be to deploy to an Iris GTX smart camera. The camera becomes sort of like your inspection appliance device. And option number three would be to deploy to a desktop grade platform like the Foresight. But in this case, you don't need a GPU. The inference or the prediction is running on the CPU. And you can do that again with frame grabbers or Gigi cards like the Matrox Concorde, right? So those are the deployment options. So what we have today for you folks is it's a complete set of library that is available for trial today. You're able to download it from our website. We have a Vision Academy courses. Vision Academy, it's a online training platform, sort of like YouTube, if you will, where we have a set of courses that will take you from getting the data set, training it, deploying it, and testing it. It's all video guided. We also have training, software training, as well as we actually have a step-by-step workshop with a full set of data sets that you can get started with on your journey of trying deep learning on your application. All you have to do is to contact Tim or myself. We'll be more than happy to send you this material. And I guess just to conclude, again, we're going to see compare and contrast what we call deep learning versus traditional machine vision tools. Again, the advantages of deep learning is that it handles variability very well. We saw on the PCB example, right? It handles product alignment, rotation, lighting variation, shadows, edges, noises, acceptable product variation. So that's something that traditional machine vision, it's very rigid, would not be able to do. It pays attention to the smallest of details in an image. That's very amazing. I've seen images where just the small detail is actually being picked up by the neural net. And it truly mimics a human inspector, right? So a person that you train with, images, examples of what good and bad would be, that would be the equivalent of the neural net. And again, it's good to classify defects without specific shapes, right? We're talking about organic food products, scratches. We talk about a resistor that might be slightly bent, but it's still good, right? So this is some of the advantages of deep learning. The disadvantages, I don't know if you want to call it disadvantages, but some of the things that you might have to consider is that, first of all, it requires you taking many images to train, right? Talking about 30, 60, 100, the more images, the better, right? More images per class. The other thing is that debugging a deep learning application can be very difficult because, don't forget, it's a black box. And the only way that you can actually improve your results is by adjusting your data set, perhaps adding more data, right? So that's one of the drawbacks. It's not like traditional machine vision where you can move a slide bar and have a different threshold and see what those results are, right? So that's one of the things that we need to take into account. And of course, it does require very careful data preparation on the data set to avoid biased results. When we talk about thousands of images, right? It's some cases that you could maybe have a image categorized in the wrong folder or a few images. So again, have to be very careful with that. And like I said originally, it may require multiple trials. That's where the GPU comes in handy because you're gonna have to wait for a long time to see the results of the CNN. The good news is that Matrox offers both deep learning and traditional machine vision tools. So that's one of the greatest things of the Matrox tools. You're able to tackle applications using both of these tools, right? So in conclusion, let's see. So first of all, to build your application, we need to define your deep learning application. We need to define if you're going to use so first of all, you need to define if you're going to use deep learning or traditional machine vision, which is very key. We've seen applications where originally the request was to try it with deep learning, but at the end, we're able to resolve it with traditional machine vision tools. So that's the first thing to determine. But once we know that it's a project for deep learning, we need to understand if it's going to be global classification or segmentation. We'll need many samples per category. That's important. The more images, the better. As you can see, Matrox provides the entire workflow, both on the software and on the hardware side, to build machine vision inspection applications using deep learning. There's the, basically Copilot, which is menu-based and design assistant. Again, this is no coding interface to develop deep learning applications, so no need to learn TensorFlow or some of those other programming languages. You can do everything through our tools. And what you end up, our solutions are adapted to run on cost-effective platforms, right? So we're talking about the Foresight EV6 or the Iris GTX. You don't need a supercomputer or a GPU system or multiple GPU systems to run applications. As we mentioned, we offer improvements of your CNN with the fine-tuning process, as well as another training called transfer learning. And again, Matrox has this an extended tool set of 2D and 3D vision tools. And like I said, we have training and the workshop available today. If you want to get access to the data sets and training material, all you have to do is to contact Tim or myself, and we'll be more than happy to assist you. And with that, we conclude the presentation. I'd like to thank you very much. I guess I'll pass it on to Tim. I know there's a few questions on the chat box.
We've had questions rolling in. Thank you, George. Excellent presentation. I think it was definitely clarified some of the terminology that we're coming across every day. That's for sure.